Hello everyone, I'm Giuseppe Maggiore and welcome to the final piece of the final lecture on generic classes. Today we're going to talk about how to produce the same kind of classes that we used from existing libraries, the generic collections, the immutable generic collections, the functions, the tasks, etc., which are just given to us, how to create them ourselves. So we will look into how to create custom generic classes. Let me run the build in watch mode, always useful. Well, okay, no real reason to run this program at this point, but whatever. And here we go. Okay, now, any single construct that we have in C# can be made generic. Any construct in C# can be made generic. What do I mean by construct? Well, any construct, any declaration we have seen of something with a bit of structure. So variables cannot be made generic, for example. Like you have a variable and it is of a given type and that's it. But functions can be made generic, classes, records, interfaces. Any abstraction construct can be made independent, I should better say parametric, with respect to one or more type parameters. So, for example, let's say that we want to define a function that creates an array with n elements with the same value. Okay? So let's look at this function. Let's say that we start with integers. Let's call this function repeat. We have the value that we want to repeat. How many times do we want to repeat this? And then, well, we could concatenate stuff and make it very cute, but I'm going to chill a little bit. I'm going to keep this as simple as possible. So the result will be a new int array, and then for I from 0 to times, yes, what do we do? Well, quite simply, result of I is equal to value. So what do? We just copy the value on every element of the array. What if we wanted to turn this? So let's actually call this repeat int. But what if we actually wanted to do this for strings? Okay, then of course this will be repeat string. The value will be a string and not an int. The result will be a string array. This thing looks exactly the same as the previous repeat function, but what is the real difference? What is the only difference? The difference is in the type, int between string. You can imagine that there are infinitely many functions that basically look the same, that we can just copy paste and just change the type. Why infinitely many? Well, because there are infinitely many types for which we might want to create such an array. Because we really want to be able to capture patterns in code to reduce repetition, reduce the size of code, so there are less things that we have to think about, and also changes can propagate along the patterns more quickly throughout the whole code. It is possible indeed to capture this sort of repetition. What I'm going to do now is I'm going to splice the code so that we can actually observe the bits that are actually different. Okay, so of course the declarations are different, so we will need to do something, and also the variable result that is different. The for loop is exactly the same, the returning the result is exactly the same, the closing curly bracket is the same. Okay, so what is different here? Well, what is different is the type, int, string, also here, int, string, and of course also here, int, string. In C# it is possible to define a function by stating that the function takes as first batch of parameters between these symbols. So this you shouldn't see as a smaller than and greater than, but rather as angle brackets. So these are special brackets because they group together the type parameters, whereas the normal brackets group together the value parameters. And between those brackets, you define a parameter, which is just literally the name of a type. I can call it here t. This is quite common in Java, C# land. I could also call this, I could also give it a more expressive name, which is actually not a bad idea. Or I've also often seen something like this, t element, meaning the type of the element, in this case of the array. Then I can use this wherever I want. And there goes the declaration. And here, inside the body of the, actually, everywhere in the scope of the function, also a little bit crazy, to the left, so before the element is introduced, we may use it already to the left of the name of the function, but in the whole scope of the generic function, so everywhere, we can now use the element as a type. So I can use it like this. And now repeat is a generic function. So I could say that I get a bunch of ones, and I can call repeat. And now the first thing I pass is the parameter, the type argument, and I put it in the same set of brackets. And now you can see I have to specify a value. Well, it's a bunch of ones, so that's 1, and I want 10 ones. Okay. Let me print with a comma as a separator the ones. Let's see what happens. Let's run the program, and we should get, well, a bunch of ones. Okay, very good. I could also say that I want a bunch of hellos. Now, this is going to be a string, and what I do want is hello. And now I join the hellos. Let's run this, and unsurprisingly, we get 10 times hello. Okay, very good. Now, and of course, this approach, this repeat function, this generic function, well, we can use it for whatever types we want. We could have a record, let's say person, with the usual string name, string surname, and here we can create a bunch of gyms, and that's of type person, and here we can say, I'm keeping it to 10, but it doesn't need to be 10, of course, gym, disegno, and there you go. Now, if we were to try to print this, to print the gyms, actually let's have less gyms. Okay, now we get a small problem because because also join is a generic function, and there are 2 versions, but I'm going to use the proper one, the one that actually knows the type, rather than the one that casts to object. And you see, gym disegno, 3 times. Very good. Okay. Of course, well, we've seen primitive types, we've seen a custom type. You can imagine we can also have arrays, we can have tuples, we can have whatever we want between the angle brackets. Something that's also interesting, though, is that we don't always need the angle brackets. There is a mechanism which is very powerful and works quite often, but not always, which is the so-called type inference, meaning that C# is capable, just like for var, to guess the generic type arguments. So if we hover on top of gyms, it actually knows that this is an array of person. Hellos, it's an array of string. And ones is an array of ints. And also, if we hover on top of int, you can see that the type argument here has actually been guessed correctly, but it's there. It's not like we're working with a dynamic collection where the type may change. No, it's still statically typed. The compiler is still very strict, but we don't need to specify everything ourselves. When we combine generics and polymorphism, interfaces, etc., then we have to be specific. We've also seen it when we dealt with arrays and polymorphism. Like then we simply have to put the type arguments explicitly. All right. We can, of course, define more complicated constructs. So this is a generic function, very powerful. But suppose that actually we want to initialize the elements based on their index. Like we want to, instead of just repeating an element, we want to do something a little bit more sophisticated. So instead of repeating, we want to say, well, init array, okay, and now, instead of getting just a value to repeat, we get a function that, given the index of an element, gets the value to put in that position. So of course, when filling element I, we call the getValue function with parameter I. And let's say 1 to 10 would be the initialization of an array of int. Of course, now we get a complaint because well, 1 is not a function from int to, in our case, int. And so we have the index of the element to calculate, and you know what? I'm just going to return I back. So 1 to 10. So what does this do? At position 0, it will put element 0. At position 1, it will put element 1, and so on. Let's take a look. And we get 0 through 9. Makes perfect sense. But we could also say 1 to 20 evens. And now this could be I times 2. I'm really trying to give descriptive names to these pointless arrays. And when we run this, we get 0, 2, 4, 6, etc. up to 18. So we can now calculate the current element. This pattern, this combination of lambdas and generics is extremely common. Why? Because if you look back at the repeat, what do we know about the element? And what do we know about value? Nothing whatsoever. So the only thing we can do is basically it's the game of put the square peg in the square hole. You know, it's quite silly how limited the generics are without lambdas. So here, what I can do is simply put the t element into an array into the elements of an array of t element. That's all I can do. I can just copy. And the only thing that C# actually allows us to do is to say, okay, you have a t element here, and this is a t element. Okay, you're allowed to put it there. But if we try to do anything with the value, say value dot, there's nothing. Okay, there's only the stuff that every single type has. Equals, get hashcode, get type, and toString. But what if I want to, for example, create a new t element? Well, then I need to provide a function, and this function, in the case of, for example, getValue, is sort of like passing a constructor of t element, whatever t element might be. So here I'm kind of stating that t element can be constructed based on an int. And if I want to do things like, for example, I want to be able to take two t elements and I want to say I guarantee that they can be concatenated together, then I will have to pass, I'm not going to use it here, but just to give you an impression, if I want to be able to concatenate the t elements together, actually, well, okay, this is a more sophisticated way to initialize an array. It would be init array, or this would be an unfolding of an array. So we get an initial element, and then we have a function that takes the accumulated element and the index and produces a new one. So that's the next value, and for a bunch of times. Look at this. This is actually very cute. Of course, now getValue doesn't work because we also need an accumulator. Current element. Yeah, current element. We start with initial element, and then when we call getValue by reassigning the current element. Oh, and this is a get next value, and then we put the current element here. This is actually very cute. Or we can decide to put it after. So basically, we start with an initial element that goes into result of 0 or result of 1. This is this is a matter of preference to an extent, and also what you're trying to achieve. And then we use the current element to calculate the next element, which could say, okay, add 1, add 2, multiply by 2, etc. So this is a very powerful way of generating values. So, for example, we could generate the something like, for example, the Fibonacci sequence. But I don't want to. I actually don't want to do this yet. But let's say here we get the index, which we don't really care about, and we get the previous element. Let's call it. That's kind of the state of the computation. Then we multiply by 2, and now we're generating sort of a progression of powers. Okay, no, this name makes no sense anymore, and I'm not going to bother, so I will call this just a bunch of ints, very bad name. Okay, now we get 1, 2, 4, 8, 16, etc. So this is creating the powers of 2, but it's creating the powers of 2 in a very efficient way, because it's creating the next power of 2 based on the previous one, which is actually quite a good way to go about this. Or indeed, the example I just made of the Fibonacci numbers, you could say that you start with 2 Fibonacci numbers, whatever, let's do this. But I will accumulate the previous, so the current and the previous. We start at 0, 1, and then here, instead of S, we have the previous and the current Fibonacci number. And what we return is the current gets shifted, and here we have previous plus current. Oh my god, the IntelliSense is really angry at me. And why is it unhappy here? Okay, let's call it state. So state.item 2, and this is state.item 1 plus state.item 2. I was hoping that the composition would work. And if we now run ints, then you see that we have that they're growing. And now what we could also do is we'd simply select, and then for every pair of items we simply select item, I would say item 1, and then convert back to array. So instead of having the tuple of previous and current, because those overlap, so previous and current, but then previous and current, and then the next previous and current still overlap. So now we can simply keep the first element, and this would be the Fibonacci sequence. What am I doing? What happened? Oh. And there you go. So 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. But this is also a super fast way of calculating the Fibonacci sequence, because in order to get to, I don't know, 1,000,000 Fibonacci numbers, you're using the previous value. And you just add 2 things together and you get the next, add 2 things together and you get the next. Fibonacci numbers are famously very tough to calculate if you do it in a naive way with recursion. All right. Now, it is possible to also apply genericity to data types. So we can have generic classes, we can have generic interfaces. And actually this is what we are going to do next. We are going to create a generic records, of course, being a shorthand for classes. Let's say that we want to be able to represent values that can be either let's say we want to represent values that might not be there. This is what we call an optional value. An optional value, we start with an interface, and then we have 2 variations of this interface. Sum of the value, which actually does just contain the value, and implements iOption of the value. And then we have none, so no value, still generic. Wait. Well, This is quite a peculiar way to guess, but okay. No, I don't want it double. Come on. Ah! Okay, very good. And this is an I option of t value. It got me. This doesn't belong, of course, because none means that there is no value whatsoever. Okay, so suppose we have a function, let's say a safe divide. I don't know if you remember, but we want to attempt a division, and we really don't want this to crash. So we get two numbers, a and b. And now, if b is equal to 0, then we return a new none, because there's nothing to return. None of int. Okay. Otherwise, we return a new sum of int, and this will be a divided by b, which actually happens to be perfectly safe. Now, if we call safe divide of, let's say, 10 and 0, let's see what happens. We simply get none. A very common practice is actually to define the generic functions sum t value, which takes as input the value, and actually just returns new sum t value value. Okay, why is it unhappy? Okay, sure. Oh, and there is no return statement, of course. How silly. And of course none. And this way, well, first of all, generic functions have slightly better type inference in C#, so I'm not being silly, and also because it saves us from this slightly ugly, because none and sum are just concepts, so you don't want to think about the container data types. And of course, if we actually want to be able to see what came out of this, we can always switch, and we can say, okay, switch on some value, and then I can simply say, okay, just put the value. Sum of int value. And, oh, wait a second, come on, this must be possible, yes, and otherwise, we can simply say, okay, there was an error. And now, we should actually just get error, because we're switching with a pattern matching on the result, but if we divide 10 by 3, then we just get 3. There you go. I option happens to actually be a useful pattern, so it's not only a good example for showcasing generics, but it's also a very useful pattern in practice, which is part of the foundation of many type-safe and in general safe programming languages. One of the cool things about generics is that generics really force you to think about richer data structures, because generics applied to trivial stuff don't really make any sense. Like there's no use of generics outside of very general purpose constructs, and usually those are collections, manipulations of collections, manipulations of functions and threads, etc., which makes generics interesting, powerful, unmissable whenever you're trying to achieve something serious with your code, but also at the same time, and this is one of the downsides of generics, quite hard to explain and learn, because in order to learn generics and appreciate them properly, you actually have to be quite familiar with the complexities of the things that generics actually help you manage. All right. Now, another data structure that I wanted to show, which is a variation of option, is either. I'm actually going to copy either, and either is a way to say that you have a data structure that returns either one or another value. And these values are called left and right. I'm not a big fan of these corporate programming names. I'm just going to call the names L and R, which is left and right. Feel free to call them left and right in your code. So left of LR contains a left value and implements either of left and right. Right, on the other hand, being almost identical of LR, takes as input the right value and implements either of LR. You might realize that actually, if we say that left is some and right is none for the right value, which is irrelevant, like something empty, like I don't know, a tuple without anything, or just an empty object that you always put to null, then either actually happens to be a strict superset of ioption, and you could actually implement ioption with either. But we're not going to do that today, because that is a little bit too much. Now, we can also define this sort of constructors. So you could say we have left, we have right. Of course, we have two types, left and right. In order to initialize left, we need to provide a left value, left and right, just the value. And here we also provide the value. This will be right of left and right. A bit tedious this, but well, it is life. Now, interestingly, we could also decide to have both of these simply collapse down to either of left and right. Is also one interesting option. I wouldn't be able to tell you which one is better, because you could, and of course the same applies here, to say that if you call these constructor functions, you actually lose the specificity of this information, on the fact that it was left or right. Because if you call new left, okay, you really want to know that it's left, but if you call these functions, you just want to forget about it and just collapse down to either or option. Okay. One of the best uses of either is optional result, where we could say that, okay, optional result has again a single value. You know what, I will call it v, because I'm tired of typing stuff like t-value. And this implements either of, we could say v, and for example, we could say that here we carry an exception around. So we could say that there's a way to have a result or an error, and that would be of type optional result. So I could say, okay, optional result, and this could be success or result, say just a result, and this gives us an and for this, of course, I just call the left of value. Yeah, okay, left of t-value and exception. Oh, it's unhappy. And what can't we convert? Let's see. So, cannot implicitly convert either t-value system exception to optional result. This does surprise me a little bit. It should definitely make sense. I was expecting this to convert automatically, but anyway, you've seen the pattern. Hopefully this is enough, and then apparently I need to convert this to an optional result of t-value. Okay, whatever. Still a bit unhappy. Possible null reference return. Yeah, okay. I don't know why it's being so fussy about it. Anyway, we might even decide that either is the type we always use. This would be a bit excessive, but I still want to show the pattern. We might want to decide that either is always used for a result and an exception. So we could say, we could add a so-called generic constraint. In generic constraints, I can put a lot of things. I can say that a type has to be a struct, has to be a value type, has to be a reference type, has to implement an interface, whatever. So in this case, I'm going to say that R has to implement exception. So now, and there's a slight complaint here, again, for the same reason. Okay, I always hesitate a little bit, as you've just seen, about where are you supposed to put the type constraint. And here, of course, we are going to add the same constraint. There you go, yes. So now I could say I either of int, and if I accidentally were to say, okay, this is an int or an int, no, this is not good, because the right side has to be an exception, or has to implement from exception. So if I provide a class my custom exception, which inherits from exception, for example, and I put my custom exception here, well, now I either is happy. Of course, none is not happy, because now we have to return a right instance. And I'm wondering if, yes, okay, this was smart enough. And not A. I really don't want, yes, okay. Right is being a little fussy, so unfortunately, no, there you go. And here we return left, again of int and my custom exception, and there you go. Slightly disappointing me. Okay. Thanks to generics and generic constraints, it is actually quite, interestingly possible for us to define a container that only accepts parameters of a given substructure of types by combining therefore generics and usually polymorphism and inheritance. Very cool, very cute. Let's play a little bit with so-called generic combinators on top of the I option. Now let's actually bring this all together in an advanced scenario. All right, so let me first remove the either. I think we've seen it enough. Yes, okay. And let's see how to define some utilities around this type. First, the obligatory, let's get the compiler to stop complaining. Yes, very good. Okay. So, for example, we could write a for each function that iterates through all the values contained inside an I option. Because if you look at I option actually, and you know that I option is either sum, so one value, or none, you can kind of see the I option as a container. But yeah, instead of a container like the list or array, which can contain an arbitrary number of elements, it can contain at most one. Still, it's possible to for each on top of it. Now, for each, then, well, this has to be generic, because the ability to iterate on top of an I option doesn't really matter, isn't really dependent on whether or not, well, the type argument of the I option. Okay, and now we can say switch value, and then, well, in case we are dealing with some t of value, and then we break. Otherwise, no, we also break. And here we have to call the body of the we have to call the body of the loop on top of value. Here there is nothing whatsoever to do. Okay, but what does the loop actually do? Well, this has to come through a lambda, and this lambda, let's simply call it, the body, or if you want, on a value, because it's kind of a callback that is only invoked when there is a value. I will leave it to you which one you prefer, and here we simply call body on the value, because the body of the loop has to be executed at least once. And so actually let's go back to the save divide operation that we had. So int a, int b, and if b is equal to 0, then we return none of int, otherwise we return sum of int of a divided by b, because it's safe to do. Okay, and now we could call for each, and what do we pass to for each? Well, we pass a safe divide, let's say of 10 and 2, so this is safe, and then as an action, and actually, you know what? No, we're not going to do it here. So we call for each, and then for each value inside the result of safe divide. So if there's a value, then we say, okay, we print it, and I can just pass console.writeLine like this. And in this case, console.writeLine is actually returning a value. It's actually being passed a value by for each. But if you do 10 divided by 0, then console.writeLine is not going to be executed. So we get nothing. This is kind of funny because it's a way to perform operations on the content of the generic container, and they require the lambda because dealing with generics requires lambdas to specify what kind of operations are actually supported, and the operations that are supported is kind of like the interface around T has to be supplied in the form of one or multiple lambdas. Okay, I'm going to do something that I find very, very cute. I'm going to define a static class, and this will be the option extensions. There we go. And now we could also have a for each method here, but I actually just want to be able to call the for each method on an iOption, but I don't want to make the implementation here in sum and none. So I'm going to make this static and also public, otherwise we can't call it. And I will just mark this first parameter of type iOption with this. Look what happens now. Save divide of 10, 0. Now has for each. And extension methods, which is what we just used, are very often used in order to combine generic functions with existing interfaces to provide implementations on top of the type by sort of extending the type without actually having to do the implementation inside. It's actually very cute, this. Okay, so what does for each do? For each calls this action, but it's an action, so it returns void, it returns nothing whatsoever. It calls it on the value inside an iOption. And if there's no value, this is not called. Okay, that's a possibility. What if, on the other hand, I want actually this action here, the body, to do something, to return a value. So I'm going to add a second type of parameter. Let's call it u, and this will become transform. Okay, now we get a value. If the value is sum, then I return. Okay, what do I return? Well, I cannot return a u because if there is no t inside the value, then yeah, what do I do? So what I can return is I can return another iOption, but of u. So I'm going from an option of t, which is the source element, to an option of u. And in this case, well, the source object is full. So now we return sum of u with a transformed value. On the other hand, we can simply return none of u, and none of u we can always create. Okay, let's see what is complaining here. Some u cannot be used like this because it's a top level statement, whatever. Okay, sure. New none. And now the body, the body of course has to be a function, so it takes a t as input and returns a u as output. As it was written like this, action tu, it was simply a function that returns void but takes a t and a u as parameters. That's not what we want. Okay, and because we're returning, we don't need the break statements. Okay, now it's really worth it to give better names. In general, you should have better names. Now, this is the source type, and this is the transformed type. Okay, now it's longer, but look, we have the value. Let's also rename this to, this is the input container. Okay, so we have an input container which contains either 0 or 1 t sources. If there is one source, then we transform it via the body. Okay, so let's say transform value. Okay, very good. Then we check the input, and indeed if the input is full, then we perform the transformation, and then we put it inside another sum, because we need to put it inside the box, because in the other case, we can return the empty box. So there is no way to meaningfully return a t transformed back directly. Well, there is actually, but we're not going to bother with it. This is more than good enough. We can also continue our, okay, no, wait. So now what we can do, because this is also here marking the first parameter input with this, so actually what I can do is I can also perform a transformation. What kind of transformation? I could say, okay, if you have a value, I don't know, incremented by 1, and in our case, okay, 10 divided by 0 doesn't return anything, so transform simply takes none and remaps it into none, and then we try to print, but there is nothing because none stays none. Okay. On the other hand, if I were to divide 10 by 2, then, okay, 10 by 2 is 5, wrapped in sum, and then we call transform, which increments 5 by 1, and we get 6, and then 6 gets footage and gets printed. There you go. Kind of awesome, this, isn't it? And we can also change the type. We could say, okay, you know, take the value and turn it into a string. And then take the value, which is now a string, and, I don't know, add an exclamation mark to it. Now it's becoming a little silly. In this case, when we have these so-called fluent pipelines, which are just chains of operations, it's actually very cute, but it's a good idea to actually put them on different lines, because these are different operations, so it's good if they have the necessary space in the code, that you can actually read them properly. And now I'm going to add yet another of these operators. This is true. I find this honestly truly beautiful. Okay, so let's say that I want to be able to validate some values. Now, so let's call this validate, and validate will take as input, of course, an I option of t, which is the source or the input, and then it will take a validator function which takes as input the t if available, and returns a boolean whether or not it is valid, whether or not it's allowed. And what do we do? Well, I'm going to be lazy here, and I'm going to copy most of this anyway. Okay, so in case the input is sum of t with a value, then we check if is valid over the value, returns true. Okay, then I simply return the input, I've validated it. Otherwise, I return none of t. And okay, if the whole thing was empty, we leave it empty. And now I can say that after performing, let's say, the division, I want to only let values pass which are even. And because 5 comes out of 10 divided by 2, validate has actually removed the value and effectively stopped the pipeline. On the other hand, if we say no, the result after has to be even, well, now 6 remains because, well, 6 is even. Very cute, very pretty. And now we have the ability to build these gigantic pipelines, and look at how much generics have actually helped in making this happen. Very cool. All right. I'm actually going to close this lesson with one advanced little pearl, if you want. So when you have a generic type, like func, actually, so the question is, if I have a func of that returns an I option, and I have a func that returns sum, are they polymorphically related? And okay, let me show you. Okay, so let's say I have a function, takes as input int, returns sum of int, and this simply performs a boxing operation. Okay, so this takes as input the value and simply calls new sum of int of the value. Okay, so this is really nothing to get excited about. Now I have a function that takes as input an int and returns an I option of int. And let's call this box2. Can I put box inside box2? Actually, we can. So this is interesting because there is obviously a polymorphic relation because sum of int can be converted to I option of int. And so this function can be converted to this function because basically what does box2 say? It takes as input, gives it to box, box gives sum of int, and as box2 can simply cast the sum of int safely to I option of int. That always works. What about the opposite? Now the opposite doesn't work. Why doesn't the opposite work? Because box returns an I option of int, and an I option of int might also be none. So in this case, this function box is still type safe. It still makes sense because I just said box now creates an I option of int. And now if box2 wants to guarantee that it's able to return sum of int, but box only guarantees to return an I option of int, well, what do you know? This is not a safe conversion. All right, so this is one case. Let's do another. So let's say that we have a function that takes as input sum of int and returns a sum of int. Okay, so let's call this traverse or map. Simply lets stuff go through more or less, but let's say that this increments by 1. Okay, whatever. Okay, and here I have a function, let's call it map2, and I want to assign map to it. But this is not safe. Why is it not safe? Well, because map2 receives as input an I option of int, and this input cannot be safely passed to map because map expects a sum of int. Let's flip it around. Let's flip it around. Well, of course, now I cannot say v.value plus 1 because it might actually not work. So now I have to actually, for example, perform a check. I have to switch over the value and say if the value is sum of var value. Okay, then I actually can perform the increment. Sum of int, okay. But otherwise, for example, I could say, okay, return a new sum of int of 0. We can use a placeholder, all right. And now look, this assignment works. Why? Because now map2 gets as input sum of int. This is just passed to map because I'm simply pipelining, I'm simply assigning the functions. Okay, so map2 gets sum of int. And map, okay, map accepts an I option. So in this case, we go from sum of int to option, which is safe because sum of int is more specific than option. Then map returns a sum of int, which has to be converted back to I option. So it's kind of like go up, go right, go down. Okay. All right. How does C# know which direction to allow conversion? Well, usually when you return something or when you contain something, we say that that type argument is covariant. So in our case, from more specific to less specific, from more specific in the container, less specific the container. And things that are given as input have to be contravariant. So you can give something more specific and you can convert to something less specific. That's possible. This is actually done with the two little keywords in and out. So basically, out means it's a container, so the func is polymorphic along the same direction as the result, and in means that it's contravariant, so func is polymorphic in the opposite direction. And actually, let me see if I can conjure this. Let me create a new list. There we go. List of int doesn't really matter because list is a container. Yeah, no, okay, it doesn't matter that much. In list, arguably, t could have been. Let me see if IEnumerable is more forgiving than this. Yes, in IEnumerable, you can see that the type parameter is marked as out, just like the return type of the function, because indeed, if you have a list of, if you have an IEnumerable or a list of sum of int, you can cast it, you can convert it to a list or IEnumerable of I option, and that is safe. But obviously the opposite is not the case. And the last one that I want to show is the definition of task. Oh no, come on. Okay, task of int. And actually this surprises me a little bit because I was honestly expecting the t-result to actually be covariant, but it doesn't matter. Okay, it's up to the function to the library maintainers. So, and this kind of is the cherry on top because it shows that generics are strictly related to containers, and there are two ways of having containers. You have containers where you put stuff in, and that would be the contravariant aspect, like the function where it's a container where you put something in, and that's the first generic argument, and you get something out, and that's the second generic argument. And the get something out of it is what we associate with a traditional container like a list. And the put something in, that's usually what we associate to like a pipeline that actually gets an input to process. I can imagine that I can imagine honestly that generics might feel a bit daunting. The ability to represent complex, rich types can only be fully appreciated when you're trying to actively build algorithms that are supposed to work with the different data types. For example, if you want to create an algorithm that performs a synchronization between two completely different CMSs, let's say Drupal, WordPress, or Strapi, then you will need generics very much because you will need the ability to abstract over the underlying data types. But until you have to face these issues, then this might feel a little bit theoretical. That's okay, that's all right. It's good to know, it's good to learn, and eventually all the pieces will click together and it's going to be a wonderful feeling. This brings us to the conclusion of the introduction to C#, at least the theory. Thank you so much for being here. Thank you so much for enduring all of this. I understand C# is a huge language. We've seen basically all of it, and now you still have to learn all the frameworks and the libraries and the design patterns, etc. Give yourself time, you can do it, but especially don't forget to have a lot of fun while you're doing this. Thank you once again, and see you soon.